Okay, so let's start chapter 7. Chapter 7 is about sampling and sampling distribution. I think this chapter probably is the easiest, but the most important chapter to the rest of the course, and probably to the rest of the quantitative management course as well. Okay, what is sampling? Remember, we have a population, okay? And from the population, we are going to have a sample. For the populations, we have parameters. The parameters are mu for the mean, and again, I mean, this is not an M. This is a mu. It's a Greek letter, mu. This is sigma. This is the standard deviation. It's not an O. It's a sigma. So for the parameters, we have the mean. We have sigma, that is the standard deviation. And for the sample, we have statistics. The statistics are X bar for the mu and S for the standard deviation. Okay, so if I tell you mu, it means that is the mean of the population. If I tell you X bar, it means that is the mean of the sample. Okay, so when we sample from a population, we want to make inferences. Remember the two branches of statistics, descriptive statistics and inferential statistics. Previously, we have been covering descriptive statistics. This chapter starts with inferential statistics. We are going to try to infer something from the population based on the sample. So the sample has to be a representative sample from the population in order to do right inferences. Okay? So we need to have a representative sample in order to make good inferences. Now, why we sample? Because we need to know something about the population. For example, if I produce light bulbs, how long my light bulbs last? I have to sample and check them and see how many hours those light bulbs last. 3,000 hours, 2,000 hours, whatever it is, but we sample in order to know how many hours that particular lot of light bulbs last. But sometimes it's so why don't we check the whole population? First of all, it might be impossible to check the whole population. It might be very cost, or it might be like the light bulbs. We cannot test every light bulb to see how many hours it lasts, because at the end is what am I going to sell if all my light bulbs are worn out? I mean, there are some times that the sample is destructive. So you cannot test the whole population. So you use a representative sample and to get the population, to get the inferences about the population. We have two types of sampling. Probability sampling, and non-probability. Okay, non-probability samples are those samples that are especially convenient samples. Convenient samples are usually what is used in social sciences, because that's how we get our samples, convenience. Let's say that I'm interested in the population of students in the United States. What am I going to do? I'm going to use you as a sample because it's convenient for me. I have you already here in this room. Okay? So it's convenient sample. Is it representative? Well, we try to do it, but the only way that you can have a representative sample is through randomization or probability sample. But many times you agree to have a convenient sample because that's the way it is, and that's easy, and it's faster, and you try to have a representative sample from a convenient sample some way. So in probability sample, each element on the population has a known, not equal to 0 probability to be chosen. Okay? It don't have to be the same probability, but it has to be a known, not equal to 0 probability to be chosen. Okay. There are 4 types of probability sampling. That is probability, random sample, simple random. Okay, what do you do when you have simple random sampling? You generate random numbers, and from the random numbers you get the element from the population such that it is just like what? Random. It's completely random, the selection of people in the population. The other is systematic. In the systematic, I have a list of all the elements in my population, and I need, let's say that I have 1,000 elements in my population, and I need 100. What am I going to do? I'm going to skip 9 and get 1, skip 9 and get 1 from that list. So you skip the number of elements and then you select 1. And it's completely random as well, especially when your list is in non-particular order. How do you make a list of non-particular order when you're dealing with people? Just, sort the list by alphabetical order. And then you have a random list. So that's how you get this systematic probability sample. Stratified and clustered are the other 2 types of probability sampling. These 2 are very similar. In what way? Well, in both stratified and clustered, the population is subdivided in groups. And then from each group, you select the number of elements for the sample, right? But that's it. The difference in a stratified sample is that you have homogeneous group. Like what? Let's say that in my population we have different economic, not economic, let's say different different groups that are very similar. For example, we have students and we have people that work and we have people that are senior. So I divide my sample in those groups and then I select randomly from those groups a representative sample from those particular groups. So I know that each group is represented in my sample, right? That is the stratified sampling. In the cluster sampling, we also divide the population in groups, but those groups are like mini populations by themselves. For example, let's say that I'm interested in the big cities in the United States. So instead of going to Dallas and Chicago, LA, Atlanta, that are big cities. I select one big city and make my sampling in that city because that city is the whole representative. I mean, it's a subgroup, which is a mini population of the population by itself. Okay, so in a stratified sampling, we have homogeneous groups. In cluster sampling, we have homogeneous groups. So we have a mini population in here, and stratified, we have populations that are very similar to each other. Since we sample and make inferences about the populations, we can make mistakes. We have errors, okay? And we have two types of errors. So we have errors, of course, because we make inferences about the population, so we have errors. What are those errors? Sampling errors and non-sampling errors. Okay, the definition of a really sampling error is basically the difference between X bar and U. That is my sampling error. The difference between the statistics taken from the population and the real population parameter. That is a sampling error. That is the definition of that sampling error. It's the difference between the parameter and the statistics. How do you correct the sampling error or try to minimize the sampling error? The best way to do it is to increase the sample size. So increasing the sample size, you reduce your sampling error. In the non-sampling errors are really systematic. What does systematic mean? I mean, why systematic errors? For example, if I tell you I am representing the Association of the MAD, or Mothers Against Drinking and Driving, and I ask you, what do you think about, drinking a couple of beers and drive? Since you know that I belong to that association, what is going to happen? You're going to tell me, you shouldn't be. I mean, it shouldn't happen, whatever. So, but in reality, it may be that you don't think you create that error because of the circumstances. So it's a systematic error because there is no way that you control it. The only way that you control a systematic error is through the methodology. Is to be sure that you do not influence the other guy. Or something. I mean, there are sometimes that you create your own errors, your own sampling errors, and there is no way to detect them. There is no way to correct them, but through methodology and through realizing that what you are doing wrong. So it's very hard to detect and correct those non-sampling errors. Okay? So far so good. So sampling is extremely important. We need to have representative samples, and sampling is going to serve as inferential about the population. So it's extremely important. We have what is called the central limit theorem. Central limit theorem tells you that, well, hold on. whenever you sample from a population, you generate what? Let's say that you are dealing with a population, and you sample, and from the sample you get X bar, right? Because that's the statistic of the sample. And you want to infer what is the value of the mean or the mu. From the mean of the sample, you want to infer what is the mean of the population, right? So the central limit theory tells you that whenever you sample from a normally distributed population, your sampling distribution is going to be normal. Okay, so hold it again. Whenever you sample from a population, you get X bar. What happens? And you get a sample and you get X1. But you sample again. Let's say that I'm interested in your age, in the students of GSWH. So I sample you and get an age, 22.3. Then I go to the next classroom and I get another sample and I get another. Not every time that I sample something, I'm going to get the same result. For you, let's say that I get 22.3. For the other classroom next door, I might get 23.7. For upstairs, I can get 19.3 or whatever it is. So every time that I sample, I have a different number, right? And it's the same population. We are dealing with the same population, but every time that I sample, I get a different result. Now, these samples behave like a random variable. This sampling behaves like a random variable, and that is why it's called the sampling distribution, because the sampling itself is a random variable. Now, the central limit theorem says that if you are getting the sample from a population which is normally distributed, my sampling distribution is going to be also normally distributed. What happens when your population is not normal or not normally distributed? And again, normally is the bell shape. 4. That's normal. It's not normal because it's normal because it follows a normal distribution. Guys, be aware of that. When you are sampling from a population which is not normally distributed, if you have a sample size big enough, the sampling distribution is normally distributed. Okay? So, it really doesn't matter where you get the sample from, what population. It really doesn't matter if the population is normally distributed or not. When you have a sample size big enough, my sampling distribution is normally distributed. Okay? So, and what are the parameters of that normal distribution? Or that sampling distribution? So we have a sampling distribution which is normally distributed. Okay? So what does it mean? And we have the mean of the sampling distribution and the standard deviation of the sample distribution. So let's do it again. When we sample, and every time that we sample, we have a different number. So this variable over here is indeed a random variable. And that random variable behaves in this way. If we have a good sample size, and guys, a good sample size is bigger than 30, so it's not that hard to get. If my sample size is bigger than 30, my sampling distribution is going to be normally distributed. So it's going to be a bell-shaped distribution with the mean equal to the mu of the sampling distribution of x bar and the standard deviation. Okay, what is, in the long run, the mean of the standard of the sampling distribution? The mean of the sample distribution in the long run is going to be the mean of the population. Okay, remember, this is the mean of the population, and this is the standard deviation of the population. And what is going to be then the standard deviation of the sampling distribution of x bar? Is going to be the standard deviation of the population divided by the square root of n, where n is my sample size. Okay? Please try to understand this. I mean, we have a population. From the population, we get a sample, and every time we sample, we generate a random variable, and the random variable is a random variable that behaves, is normally distributed with the mean equal to mu of the population where I draw the sample from, and the standard deviation of this normal distributed sampling distribution is equal to the standard distribution of the population where the sample was drawn from, divided by the square root of n. And that is why, and the standard deviation of the sampling distribution is also called the standard error of the mean. So how far away I am from the real mean of the population. And that is why if I increase my sample size, the error decreases. When I increases okay, this is this sigma of x bar, right? But if I increase the sample size, the distribution becomes like this. I mean, thinner and taller, because the standard error goes shorter. When you increase the denominator, you decrease the number. So it goes up because the standard error goes shorter. So it goes like this. So by increasing your sample size, you reduce the sampling error of the mean or the standard deviation of the sampling distribution. Okay? That's basically how the increasing the sample size, you reduce the error. Okay? So, guys, and since this is a normal distribution, and you have everything because you already know what is the mean of that distribution, and you know what is the standard deviation of that distribution, okay? Then you use what we learned the previous chapter about probabilities and the normal distributions and everything. So we have a normal distribution with the mean equal to mu and the standard deviation equal to sigma over the square root of n, right? So it's any normal distribution. And in order to find probabilities, you have to what? Transfer this one into the C distribution, saying that C is equal to x minus mu divided by sigma of x bar, right? But mu of x bar is x minus mu divided by sigma of x bar, but sigma of x bar is sigma over square root of n. So you just translate, if you will, this normal distribution into a standard normal distribution using this formula. So you use the mean of the population and you use the standard deviation of the population divided by the square root of n. Don't use the standard distribution of the population, because we are not dealing with the standard, with the distribution of the population. We are dealing with the the sampling distribution. And the sampling distribution, the standard deviation of this distribution is equal to sigma over square root of n. Okay? You got it? More or less? Good. Okay, and the last part of this section is when you use what is called the finite population correction factor. So, you know that sigma, or the standard error of the mean, or the standard deviation of the sampling distribution is equal to sigma over square root of n. Okay, don't forget that. But what happened? Remember, we are dealing with a population and we are sampling from that population. What if we have a finite population? If we have a finite population, then the standard deviation of my x bar is equal to sigma over square root of n times the square root of n minus n divided by n minus 1. So this term over there is what is called the finite population correction factor. Finite population correction factor. When we have an infinite population, when we have an infinite population, we use the formula directly. But when we have a finite population, we have to use this finite population correction factor that is equal to the square root of n minus n divided by n minus 1, where capital N is the size of the population, and low n is the size, or the size of the sample, or the sample size. Okay? Capital N is the size of the population, and slow n, or lower n, is the size of the sample. How do you know that is a finite or infinite population? Well, when the proportion of the sample divided by the population is greater than the 5% or 0.05, then we have a finite population. And we have to use this factor. Think of it, think again. When my sample size is 5%, it's more than 5% of the size of my population, then we have a finite population. Otherwise, consider this as an infinite population, and don't worry about that. So let's say that I have a sample size of 40, and my population size, let's say my population size is equal to 1,000. So I have 1,000 to draw the sample from. And my sample size is equal to 40. Shall I use or shall not use the finite population correction factor in order to calculate the standard deviation of the sampling distribution? Well, go that way, n divided by n is equal to 40 divided by 1,000, and that is equal to 40 divided by 1,000 is equal to 0.04. Is 0.04 greater than 0.05? No. So this is an infinite. So the sigma of x bar is equal to sigma over square root of. Okay? Why? Because only when the proportion is greater than the 5%. In this case, it's 4% or 0.04. So we are going to consider this as an infinite population. What happens if under the same circumstances, n is equal to 1,000, but low n is equal to 60, my sample size is equal to 60. What is going to happen? N divided by n is going to 60 divided by 1,000, and that is equal to 0.06. Is that greater than the 5% or 0.05? It is. So in this case, I'm going to write it right here. In this case, guys, my sigma of x bar has to be equal to sigma over square root of n times what? Times, well, we already have numbers in here. 1,000 minus 60 divided by 999. So we have to include this factor, that is the finite population correction factor, and remember it's n minus n, so it's 1,000 minus 60 divided by n, capital N, or 1,000 minus 1 is equal to 999. Okay? So be very careful on that. If I don't give you, guys, if the problems do not give you the size of the population, it means that the population is infinite. Okay? Only when the problem gives you the size of the population, you need to verify if you need to use or not the finite population correction. Right? So let's do a problem. And this problem is part of the homework, but it doesn't matter. But it's a very important problem. So let's do 710. 710. It says 710. Identify the symmetrical interval that includes 95% of the sample mean for a population, for the population with mean equals to 45. What is the population mean? Remember, what is population mean? It's mu. Mu is equal to 45. And the standard deviation equal to 9. So the standard deviation of the population, so sigma is equal to 9. Using a sample size of 36. So low n is equal to 36. So the sample size is big enough. So we may know that the sampling distribution is normally distributed with mean is equal to 45, or the mean with the mean equal to mu, and the standard deviation equal to the standard deviation of the population divided by the square root of it. So we know that this is a normal distribution with mean equal to 45 and sigma equal to 9 over square root of 36. So is 1.5. 9 over 6 is 1.5. Okay? So we have a normal distribution, right? So it's 9 divided by the square root of 36, so it's 9 divided by 6, okay? And that is equal to 1.5.
Why is the sigma there?
Sigma over square root of n? Because remember that whenever we sample, we create a sampling distribution with the mean equal to the mean of the population, and the standard deviation of this particular distribution is equal to the standard deviation of the population divided by the square root of it. Okay? So we're not saying anything about the population. We are dealing with the sampling distribution that we get 36 elements every time every time that we sample, we get 36 elements. How many times do we sample? It really doesn't matter. It's a random variable that is normally distributed with the mean equal to the mean of the population, which is 45, and the standard distribution or the standard error of the mean is equal to the sigma over square root of n. So this is it. They are asking us, what are those limits such that this area over here is 0.95? Okay? What are these limits? What are the limits of the mean of this sampling distribution? What are the interval, if you will? Now, we know that from the Z, in order for this to be 0.95, this has to be negative 1.96, and this is positive 1.96. Why I know that? Because, you can see it in the table. How big has to be this? In order for the center part to be 0.95. So this part has to be 0.05, right? The white part has to be 0.05. So this part has to be 0.025. And this part has to be 0.025, right? If you go to the table, you're going to find negative 1.96. So, from the standard normal distribution, we have negative 1.96 and positive 1.96 that set the limits where the inner area is equal to 0.95. So, but what are these limits over here? I know these limits. This is Z, this is the standard normal distribution. But what is this? Remember that whenever we want to translate any normal distribution into a standard normal distribution, we have to use C is equal to X minus mu divided by sigma, right? But what if I want to go backwards? I know my C, I know this one. What I don't know is this one over here. I have the mean, I have the standard deviation of this one, which is 1.5, right? I have the mean, that is 45, but I don't have the X. This is my X. And I have my Z. So the only way to do that is, is the same formula, but you have to use it backwards. So X is equal to mu plus Z sigma. It's the same formula, exactly the same formula, but you, instead of having Z in one side, you have X in one side, so you use C times sigma over here plus mu. It's the same formula. It's exactly the same formula. But instead of having Z in one side of the equation, you have X in one side of the equation. So the rest is easy. You just apply the formula. So the lower limit is equal to mu 45 plus C, but C is negative, minus 1.96 times sigma, but sigma is 1.5. And the upper limit is equal to 45 plus, because we have a positive 1.96 times 1.5. And those are the limits of my what? Of the mean of the sampling distribution. which I don't know whether. 1.96 times 1.5. 45 minus. This is 42.06, and this is 45 plus this one. This is 47.94. What I'm saying is that the 95% of the probability that the sample mean is going to be between 42 and 48. 42.00 and 47. That is what the problem is asking. Yes.
How do you get the 1.96?
Okay. You want this to be 0.95, right? In order for this to be 95, 0.05 has to be the rest of the distribution. So 0.05 has to be the white part. This part has to be, the white part has to be 0.05, right? But we have two white parts. So one part has to be 0.025 and the other has to be 0.025 in order for both to be 0.05. Okay? And then you go to the standard normal distribution and you are going to find the negative 1.96, 0.0257. Which gives you these numbers over here, because and since this distribution is symmetrical, then this is a negative 1.96 and this is a positive 1.96.
So you find the 1.96
From the standard normal distribution. Yes.
Okay. I thought you were like subtracting from one.
No. You get the 1.96 from the standard normal distribution table when you read it backwards. I mean, you find the 0.025 and then you find the z number. Okay? So it's very important that you understand that this is a sampling distribution, and the sampling distribution mean is equal to the mean of the population, and the standard deviation of the sample distribution is the standard deviation of the population divided by the square root of it, and that is normally distributed. When your sample size is big enough, and big enough is 30 is good.